Everybody who is all here, we are going to get started. We're going to do the chapter 12 homework. So if you haven't seen it, chapter 12 homework, let's see who's in the chat. Got the live stream going right here. We have one viewer. Let me do the pop-out chat. Mubot is here. Maybe that's the one. Noel, good to see you. What do you want to do, Noel? I was going to do chapter 12 homework, but we did that during class, right? We did some at least one problems. Mubot is in the chat. Let's throw out some Mubot points. Get the high scores right here. What should we do? I feel like I need to redo my chroma key and everything. So I'm going to re-hang up my coat on my thing. It's all weirdly... I brought a coat in, American Eagle coat. It's getting green screen right there. You can't even see because the green screen. There you go. Getting green screen. So coat, hang up. Coat, better. What should we do? Hair's looking all crazy. Homework sounds good. Can we also do a little review for the exam? You bet. Let's do chapter 12 review and homework review. So I think that would be good right there. So chapter 12 homework and reviewing for the exam. 2:20. The traffic was a little crazy this morning. Crazy traffic. Set to one chapter 12 review / MyPearson homework. Okay, this is test review and chapter 12. Chapter 12 is very much more mathy than the other chapters. Let's do it. So this first one right here goes over concepts. There are two sort of laws. We call one the law of large numbers and one the law of averages. And the way the law of averages works is it doesn't work. It's actually a fallacy. And there's a simulator that I like. I think I found it. Have I found it? Yes. So here is the simulator. And if we put someone to be a 60% free throw shooter, let's go 90%. And they shoot and they shoot and they shoot. And we'll just have them keep shooting. Now, what I want to do, there we go. Let's go there. They've made like 7 shots in a row. They made 8 shots in a row. They made 9 shots in a row. What do you think they're going to do on the next shot? They've made 9 shots in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9. What do you think they're going to do on the next shot? They're a 90% free throw shooter. What do you think they're going to do on the next shot? They're a 90% free throw shooter. Wow, Noel. Wow, yeah. Alcoa is a... That's why sometimes I start off stars like 5-10 minutes late. It's iffy. Alcoa is so iffy for me. So... I got 3 points from that. Last class they missed. But if we go by what should happen according to the simulation, what we would say is each of these free throws are independent trials. So every time they shoot, it's independent of what happened previously. This is the law of large numbers, states that independent trials do not influence the outcomes, and we'll see the long run probability. So they're going to make it. Ooh. Now what do you think they're going to do next? So no, what are you going to bet your money on? Make or miss. Type make or miss in the chat. Do you think they're going to make or miss? They just made it. They made like 9 in a row now. Think they're going to make or miss? They're going to make. I'd bet make too. They made it. So what do you think they're going to do next? Make or miss? Remember, they're a 90% free throw shooter. They're a 90% free throw shooter. So what do you think they're going to do next? This is how we learned the law of large numbers and not the law of averages. So the key is, now I don't think the last class, because last class we got burned on it. The key, and so what do you think you're going to do here? It's made 9 in a row, or 10. We're almost at like 9 or 10. Well, here's the thing. The probability they make this next free throw is what? What is the probability they make this next free throw? Don't worry about the line. The probability they make this next free throw is what? It's the probability they make it. 90%. And this is independent trials, which means, do you know what that means, Noel? When you're thinking about this, you have the information of what the probability is, which if we think about this from what we've been learning in class, we say probability of make is equal to 90%. And all of this right here doesn't matter.
It doesn't matter.
Why doesn't it matter? Because they're independent trials. So you shouldn't look at this because you know the probability they make it is 90%. So if you guess make, we're going to be right 90% of the time. But you say, but they've made it a lot. but the trials are independent. And independent means that the next outcome is not influenced by previous outcomes. So we say make, and they made it. You say, well, now they're going to miss it, right? No, that's the law of averages. The law of averages is saying that they're going to average out. So the law of averages is like, well, they've made it a lot, they're going to be more likely to miss. No, they still have a 90% probability. So we're going to say make. And they made it again. I love this is the way. So well, this is, if you look at the past, there's good questions right here. When predicting the next trial, what matters? The true probability of the event or the past outcomes? What matters more when predicting an event that is independent of other things? What matters more, the true probability or past outcomes? If something is independent of past outcomes, the true probability. If you know they're a 90% free throw shooter, even though they've just made like 12 in a row, now they miss. They'll miss 10% of the time. Eventually we'll be wrong. They could miss again. That'd have been so cool if they missed again. See, then they missed on their third. Now they're missing on like their, whoa, that was a big streak right there. They got like 14 in a row. And you can see, you can't look at the past because this occurs on the 5th shot, the 5th shot, the 6th shot, the 4th shot, the 3rd shot, the 10th shot, the 15th shot. They could go a long streak like they're doing right now. Yes. Whoa. Noel, look at this streak. Oh, that is insane. They just had a streak right here of, can I count it? They just had a streak of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. When you look, it went from 63-ish, or maybe it was about, I don't know, it was about 27 shots or so. They made 27 shots in a row. So is there not a way to predict when they will miss? Each shot has a what probability of missing, which is the complement rule. What is the probability they miss on any shot? Any shot they take, like the next shot they could miss, they just missed one, so they could miss the next. They just did. They just missed 2 shots in a row. They just missed 2 shots in a row. And they're a 90% free throw shooter. Because the previous shot doesn't in any way influence the past shots via the simulation. So after making 23 shots in a row, they missed 2 shots in a row. That's because these outcomes are. So that's what we see in this first question here. So that was a mini lecture. We're going to try to make each of these questions a mini lecture on the topics. So each of these questions is a mini lecture. The law of averages is a fallacy that things will average out, that past events influence current outcomes. That's a fallacy. That's not how we think. Law of averages is false. Fallacy means improper thinking. Law of large numbers is truth. So let's see right here. There is no law of averages. Doesn't matter. The first 5 flips do not influence the 6 flips, just like that simulation we saw. There is no law of averages. Okay, sort of similar question right here. We're turning all of these into a mini lecture so you can learn the information and also get a mini lecture from this. How about this one right here? This one, do not click on the answers. The real way to learn these questions is to not click on the answers, but to think through it. The property which states that for independent trials, as the number of trials increases, the long run relative frequency of outcomes frequency of an outcome gets closer to the true probability is what? Remember this simulation we just did? The true probability is this line. So this is the true probability. And what law states that we will get closer to the true probability of 90%? If the true probability for Miss Gallus is 90%, and as we go to larger numbers of outcomes, you'll notice, oh, quickly shoot 50. Quickly shoot 50. Notice how the line gets even closer. You can't even really tell the difference. At this point, it lets you zoom in on it by hovering over it, or there we go. She's at 89.3, and if we keep simulating further, she's at 89.3, and now she's at, what do we call this law about large numbers? Now she's at 89.8. 50% is one of the more interesting ones to do it with, because you can see, yep, I want to restart it. You can see it starts out and bounces down and it starts to go towards it. The true probability of her making a shot is 50%. And you can see she just made 2 in a row. Oh, she made 2 in a row. She's a 50% free throw shooter. It's going to be hard to make a lot of in a row now. Ooh, 2 in a row. I'm jinxed. Like, God, man. She can't make them now. 3 in a row. I should never say how many she's making in a row. So, it's... What do you think? What do we call this law? I'm genuinely interested. Because watch this. Let me see her make 2 in a row and then I'll say it. Generally. Oh, she's made 2 in a row. Okay, I didn't stop her this time. So now, large numbers, the law of large numbers. That's the law of large numbers. So law of averages does not exist. It's a fallacy that if she makes 2, she'll be more likely to miss another. That's false. If each shot is independent of the previous one, the law of large numbers states that we will see her probability in the long run. Because if you just do a few shots right here, like if we reset the simulation, let's go to 60%. It'll ask us to reset. And she made the first, she made the second. Look at, she looks like a 100% free throw shooter. She made the third. You'd be like, wow, she's so good. And you could have someone who's like a 90% free throw shooter, and they could miss the first. Yes. Yes. We just saw a 60% free throw shooter make 3 in a row, and a 90% free throw shooter miss their first shot. But what happens in the long run? In the long run, look at how they're approaching the true probability. So in the long run, once they miss, it goes back down. But if you keep simulating, they're going to approach the true probability. They might even go higher than, you might say they could go higher than that. Yeah, if you do a bunch of simulations, you notice it's at 89.8 right there. And if we do a whole ton of simulations, now they're at 90. Now they're at 90. They went to 90.1 for a moment. They were higher. But notice the probability is approaching. They're back down below 90. But they will approach the true probability. I wish it carried more decimals. Now we're back at 90. So does her probability in the long run get the value it wants? It approaches the truth. So if she's a 90% free throw shooter, her long run, in the long run, we will see 90%. This is the large numbers we speak of. The shots attempt, the more shots she makes. That is the large numbers. So like the more trials we have doing a probability, like something that like we roll a dice, we're more likely to see the true probability of the event in the long run, large amount of trials. That's what the large means, the large trials. Sample size, that's just lowercase n. Law of averages is a fallacy, it's not truth. Empirical rule is the 68, 95, 99.7, and law of large numbers is the truth. Yes, that's another law of large numbers question. This question I love a lot. It's very tricky, and it involves multiple things. So let's do this one right here. 1413. Reviewing for the test, making sure we know how to do it. A study conducted by the National Center for Health Studies found that 51% of people in the US have no landline service. Now, if you are preparing for the test, here's what you need to do with your scratch sheet of paper. Every time you get a question, you need to write down the information you have. So getting good at these questions requires knowing how to write a sample space. A sample space, not sample frame, is everything that could occur. Let me differentiate those terms. Sample space is what we use in probability to denote the outcomes that could occur, like heads or tails on a coin flip. Sample frame is from chapter 10 on sampling for all possible people or things we have access to sample. Sample frame, chapter 10, the things we have access to sample. Sample space, the possible outcomes of a trial. So what is the possible outcome here? What are the 2 possible outcomes when you look at a house and their landlines? Noel, what are the 2 possible outcomes when you look at a house and their landline? What are the 2 possible outcomes? And what we'll do is we'll make a table right here. The table makes it easier for us to understand what the outcomes are. We're going to write the event and the probability of the event. So the event is just the words of what we're saying, like heads or tails on a coin flip. And then we would write 50-50. Now, that's not this question. I'm just showing that this is a proper probability table. What are the 2 events or outcomes here that we're interested in? What would be the 2 events or outcomes? So you put your events on the left and their associated probabilities on the right, and the associated probabilities have to add up to 100%. It's a good way to write it down and write down what you know. And then you'll make sure you have a proper probability table, because the rule of probabilities are everything in the sample space has to add up to 1. So what are the two possible things right here? I'll give you a hint. What are the two possible things? There, with the color coding, that hint might help. Try to add color coding hints. What are the two possible outcomes of looking at a house and their landline? Correct. Great job, Noel. Points in the chat. So we have landline at 49% and no landline. Landline is when you have the phone on the wall, or you have a phone that, is actually connected outside. It's not a cell phone. Landlines are like what you pay for from AT&T, where you used to have service at your house. And I'd say it's even lower these days because we had a landline in Texas, but we don't have a landline here in Tennessee. So with this, we see that this is a proper probability space because the probability space, the sample space, has a probability equal to 1, as in you could add these up. You can't have a landline and not have a landline. So these are disjoint events. They're also complements because you either have a landline or you don't have a landline. They can't occur at the same time. That means disjoint, mutually exclusive. Also, they're complements because it's everything but. And we can find the probability of a complement by saying the probability of not landline is equal to 1 minus the probability of landline. And so whichever one they give us, we can just do 1 minus on to get the probability of not that event. Now they give us the probability of not landline, so 1 minus not landline is landline. Does that all make sense? Complement is always 1 minus the event. So this is the complement rule right here. And you could just see that if you solve it out differently, you could do probability of no landline plus the probability of landline is equal to 1. And then you could just subtract 1, like you could do just subtract from this side to get the other, or subtract from this side to get the other. What is the probability that all 10 of them have a landline? So this is where we have to say the word, the first has a landline and the second has a landline. And when I say and, if I say the first has a landline and the second has a landline and the third has a landline, what am I doing right here? The first has a landline and the second looks like land I'm writing. Mutually exclusive and disjoint mean the same thing, that the two things cannot occur at the same time. Come up with examples of that, like if I make an A in a class, I can't also make a C. They're mutually exclusive. If I make a C, I can't make an A. Like you can't say, I made a C in Stats 1 this semester for the whole semester, and I made an A for the whole semester. Now, a grade on Test 1 and Test 2 are mutually exclusive because you could make an A on Test 1 and you could make a C on Test 2. So mutually exclusive means if one happens, the other cannot happen, which disjoint events are mutually exclusive by nature. Complements are mutually exclusive. So what do you see down here where I write landline? Okay, so the question is, good question. What am I writing out here mathematically by saying the first has a landline and the second has a landline and the third has a landline? And this is where going to the test sheet might help out, because the test sheet, which you can use, you can't bring notes, but the test sheet has formulas. So you can use the test sheet, can't write things on it, but so we're going to go here to our exam 2 formula sheet, and you'll see very important things on here, which you can, not that one. What do you notice on here? We go to probability section. What do you notice? If I'm saying the word and, what do you notice? What? The first has a landline and the second has a landline and the third has a landline. So what do you notice? What's the probability that the first has a landline and the second has a landline and the third has a landline? Multiply. Great job, Noel. So we're doing multiply down here. And what do we need to check about them if we're multiplying? To multiply two events, what do we need to check? That's where I was saying and. So what do we need to check to multiply? Like what? To multiply, they must be what? Each thing, like the first and the second and the third and the fourth, they all have to be what of each other. To multiply them, they all have to be what of each other. They have to be independent. So this is the rule required of it. So the rule required of it is they have to be independent. So do you think the first house randomly picked would be independent of another house randomly picked? We're taking random houses. So we're taking random houses right here. Do you think the first house that we randomly select is independent of the next house? That means if this house has a landline, we pick another random house, it's not going to influence the next house to have a landline. Do you think that's true? Do you think they're independent? Do you think they're independent? that the first house we select would be completely independent of the next house, meaning that this house having a landline has no influence of another house we just randomly take. We call Brian, and then we call someone in Farragut. Brian doesn't know that person. Correct, because the houses are randomly selected. The probability of this house having a landline is not, or if this house has a landline, it's not going to influence. So the next house having a landline. What we have to remember is, to check independence, I know A happened. This influences B to happen. Dependent. This does not influence B to happen. Independent. So if we look at a quick example right here of independence, we could say, if it's snowing in Knoxville, so the probability of snow, we'll write snow. Snow is A, it's just a placeholder. The probability of snow is 1%. The probability of 100 plus degree weather is also 1%. Can we multiply these events, yes or no? So can we multiply these events and find out the probability it's snowing and 100 degrees in Knoxville at the same time? Can we find out the probability it's snowing and it's 100 degrees in Knoxville? So remember, to multiply things, they have to be independent. So we say, I know A is happening. I know it's snowing. Does that influence what I think about the probability of it being 100 degrees? Does that influence the probability? No, good, close answer. We cannot multiply them. These are dependent. These are very dependent. And so good answers right there. Let me throw you some points. So these, we cannot multiply them. That is the right answer. And we can't multiply them because they're very dependent. In truth, the probability is probably 0 or basically 0 because it can't be snowing and 100 degrees. They're pretty much mutually exclusive. Now, I know I said mutually exclusive, but we are checking here to multiply them. And to multiply them, they would have to be independent. So to check to see if they're independent, we'd have to say, I know it is snowing. Does this not influence whether or not it's 100 degrees? And it does influence, meaning it's dependent. How about with house A and house B? We know the first house has a landline. So if the first house we call house A has a landline, and this is house 1, house 2, does the probability of having a landline change if house 1 has a landline? And the answer is no. So since it does not influence the second thing, if we know the first house has a landline, these are definitely independent, which means all we need to do here to see that they all have landlines is start plugging in the probabilities and change and to multiply. So the word and, when we say it, becomes multiply, and then the house having a landline becomes the probability of the house having a landline. So now we plug in the probabilities of landline. And we simplify the equation. Simplifying the equation, we get 0.49 to the 10th power, and that is because 0.49 times 0.49 times 0.49, and that's going to be very tiny. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, that's basically 0. Let's see. That's basically 0. It gave me a very high number of houses. Oops, where did our question go? So 5 decimal places. I believe this is 0.00. Let me look at it again. And I would just ask your phone or something. We never do this many decimals. I would say, oh, Pokemon Go turned on, just draining my battery. What is 0.49 to the 10th power?
That would be approximately 0.0007979.
There we go. So I did do it right. I didn't count the first one properly. And so 79. It'll probably forgive. There's rounding on that. It rounds to 80. Really? Really? Wow. If you're off in the last digit, let me know. I didn't round it. I was like, it's point. The answer was, if you didn't hear it when she said it, it's that right there. And so I just was like, let's see if it gives it to me with the round. It didn't. It didn't give it to me with the round. So the next one is where people get stuck. What is the probability that at least one of these 10 houses does not have a landline? This is where you have to write your sentence. So when you write your sentence, we start by doing the following. Let's erase everything below. How you doing, Noel? Is it making sense? This is an at least one problem solve right here. And so these questions people get stuck on. You have to practice them. Awesome. So let's write the two events. At least one does not have a landline. Or what? Like if you have 10 houses, at least one of these 10 houses will not have a landline or what? So you have 10 houses. There's the 10 houses. So it could be that like that one doesn't and that one doesn't. So at least one does not have a landline. It could be they all don't have landlines. So at least one does not have a landline or what? Could be this. Well, so the way you have to think about it is imagine I flip a coin and I say I'll get at least one heads on the coin. Maybe. And then, so let's do this one. I'll get at least one, I should put that at the top. I'll get at least one heads, or I'll get what? I'll get at least one heads, or what? I'll get at least one heads, or what? I will get at least one heads, or what? When flipping coins. Well, so here is at least one heads. That's at least one heads. So I'll get at least one heads or what? It's easier with smaller examples to do this. I'll have at least one heads or what? Because the writing this sentence right here is the key to solving these. I'll have at least one heads or what? So there's at least one heads or what? Well, so wait. So think about this. When you flip a coin 2 times, you'll have at least one heads or what? So take a look at the visual diagram right here. So this is all like if you get heads, tails, tails, heads, 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 that's at least one heads. So you'll have at least one heads or what? Or what? Good tries right here. At least one heads or what? You'll have at least one heads or what? So look at the above right here. Because there'll be at least one heads or what? At least one heads or what? Because you have to write this. Writing this sentence makes these problems a lot easier. All tails. Yes. Nice. All tails. Yep. That's it. Nice job. So you'll have at least one head or all tails. So in this, at least one doesn't have a landline or what? At least one doesn't have a landline, which could mean 2 don't have a landline, 3 don't have a landline, or what? So what's the other side of it? At least one doesn't have a landline, or they what? So it could be like this one doesn't have a landline and this one doesn't have a landline. What would be something that wouldn't occur in the set of at least one doesn't have a landline? Or what? Close. Because, but wait, if they all don't have landlines, yes or no? If they all don't have landlines, then does at least one here not have a landline? If they all don't have landlines, then does at least one not have a landline? If they all don't have landlines. So all 10 of them don't have landlines. Well, no, then at least one doesn't have a landline because all of them don't have landlines. So at least one of them doesn't have a landline. How about, and you said earlier, exactly, and great job, Noah, right there. If they all have landlines, then that would be the other side of it, as in the other thing that could occur. Either all of them have landlines or at least one does not have a landline. Ah! Oh, it didn't drop on the floor. Hey. Oh, excuse me. I like to do, you ever have those jelly beans, Noel? So you ever have, they're the gross jelly beans, like they could be like fish eggs or like rotten pasta or toothpaste. Toothpaste one's not that gross. You ever have those jelly beans? And it could be like, this could be cotton candy, blueberry, and cherry. It's a cherry one. But it could be rotten lasagna, fish eggs, and toothpaste. Seriously, when I eat the toothpaste ones, I'm like, toothpaste isn't gross. I mean, I don't really want to eat toothpaste jelly beans, but I'd rather have it over like rotten lasagna or whatever. So if you think of this, when you try those jelly beans, either at least one of these jelly beans is gross or what? Either at least one of these jelly beans is a gross jelly bean, like the ones that you're like, ugh, or what? Either at least one of these jelly beans is gross or what? Bean boozled, yeah. So either at least one of these jelly beans is gross or what? They're either gross or good. So it could be that this one's gross one, this one's a gross one, this one's a gross one. So either at least one is gross or what? This is practicing writing the sentence right here to be like, oh, either at least one of those jelly beans is gross or what? Like, what's the other side of it? Because it could be that two are gross or they're all good. Exactly. Is this making sense right here? Either at least one jelly bean is gross or all the jelly beans are good. Either at least one of the houses does not have a landline or they all have landlines. Do you know what we just figured out a moment ago? We just figured out the probability they all have landlines in the first question. So all we do is we take this probability right here and we say, or they all have landlines. Nice. It's practice. You have to do like tons of examples. You have to say it multiple times. And then if you get to the test, you remember Braden, I think it was just like flying through these. When you get good at them, you just solve them instantaneously. And once you write this sentence right here, you plug in your probability and you can take and subtract and do this right here. And I think, let me show the full thing because I did delete, like someone's gonna be like, how in the world did you get that? And so if we go back in time, back, and we get back to where I wrote the sentence right here, what you want to do is you want to set it equal to 1. Really? I thought that would do it. There we go. At least one does not have a landline. And you can go right here, plug this in, or becomes plus because they're mutually exclusive. The equation is equal to 1. And then you plug in the probabilities and you solve out mathematically here. So all we do is take that first one minus 1. There it is right there. Associated probability. And there it is. And really, oh yeah, it is 0.0, so we could do it quickly. What is the probability that at least one of them does not have a landline? Great job, Noel. Excellent work. So what is the probability at least one does not? It had one extra zero on it. What is the probability at least one does not have a landline? So what? What's probably at least one of them? Oh, does have a landline. So the probability of at least one having a landline would be either at least one has a landline or what? We're doing that over there. At least one has a landline or what? So we have to say either at least one has a landline or what? At least one has a landline or what? Either at least one has a landline. So it's easier if you think about like, try it with two houses. Anytime you get these bigger problems, either at least, I think you got it, Noel. Because if we do yellow as having, great job, Noel. If we do yellow as having a landline, so we could say these have landlines, that has a landline, that has a landline. So either at least one has a landline or none have landlines. So it's easier when you do it with this example with just two on the screen because you can be like either at least one has a landline or none have landlines. And it's just way easier to draw it out when you do that. So either at least one has a landline or none have landlines. And then we turn this into a math problem here where we say that that's everything that could occur because it's the sample space. We change this to addition because they are disjoint. They can't occur at the same time. It can't be the case that two have landlines and none have landlines. So we can add these, and the probability of none having landlines is the probability of one not having a landline 10 times. That, oops, not raised to the 10th. And so 0.15 times 0.15, first doesn't have a landline, and second doesn't have a landline, and that goes back to the first question we were doing just a moment ago, where we were multiplying the probability of not having or having a landline, And this is going to be like 0.99 something again. 2, 3, 4, 5, 6, 7, 8, 9, 10. And there it is right there. Copy the number, bring it back over here, paste the number in, and there we go. And round to 5 decimals. Looks good. Really? What am I doing wrong today? What am I doing? Oh, we're not looking for this probability. That's the probability that none have landlines. I've done this question so many times. This is the probability that none have landlines, Or correct, none have landlines. So at least one having a landline is the complement. That was the probability. None have landlines, and we want the complement of that. There's the complement. So be very careful. Go a little bit too quickly and misread a question or two. Yep, great job, Noel. Yeah, 1 minus. And I had that all written out for anyone who says, no, Brian, you're supposed to take this over here and solve by taking this. And Noel, we got to throw you some big points for that. Let's throw you the 2,000 of the day right there. So we would take and subtract, and that's what I forgot to do if you're watching the problem. So I just didn't finish my equation. I found the probability that none have landlines, and that'd be 0.151 to the 10th power, but you're supposed to subtract that from 1 to get the complement of at least one having a landline. Very easy to make mistakes. Write out your equations, solve them all out. There we go. So that was a really good question that covered a lot of rules. This one's a much shorter question, and people just probably burn through it. But let's do it. Let's give it the justice it needs. Chapter 12 review, MyPearson. Oh my gosh. Okay, when I feed my parrot breakfast in the morning, he either grunts happily and eats it, screams and eats it, or screams and flings it at the cage. These events are disjoint. Now, what do they mean? If he eats it happily, what does that mean about him screaming and eating it? So let's just look at the first two and just say he either eats it happily or screams and eats it. Let's just look at only those. What does it mean to say they're disjoint? What does that mean? This is a review of the idea of disjoint, which also means mutually exclusive. What does this mean to say these events are disjoint? Now, they ask bigger questions, but what does it mean to say that two things here are disjoint? What does this mean? Well, kind of. And so what is the idea? Great job, Noah, right there. What does it mean? Event, scream, happy, scream / eat, happy / eat, and no eat. Non-influence. It does kind of, actually, disjoint events are very influential. So disjoint means if he screams and eats it, he can't also not eat it. So remember, the rule for disjoint, or the practice to remember what disjoint is we look at something and we say to check disjoint, I know A occurred. B cannot occur. Disjoint, which is the same thing as mutually exclusive. B can occur. So when we check disjoint, we say, I know he screamed and ate it. So if I know he screamed and ate it, he can't also happily eat it. If I know he happily ate it, he can't also not eat it. All of these things occurring right here are mutually exclusive, such as like if we talk about passing or failing or withdrawing from a class. So if you were to look at, what happens during a semester to a student either passes a class, fails a class, or they withdraw. Let's just go with these. There might be like a third one, I guess. I don't know. Who knows? So they either leave the class, fail the class, or pass the class. And with this right here, if somebody passes the class, can they also fail that class? Are these events mutually exclusive? What do you think, Noel? Is this mutually exclusive occurrences right here? Like if I know, which means disjoint, I know someone passed a class. Well, no, they are mutually exclusive, because if you pass the class, you cannot also fail the class. So that makes them mutually exclusive. The way I like to do it with my thumbs, I say, I know someone passed. There's no way you can fail that class, because if you pass, you can't fail. It excludes failing. It's disjoint. Does that make sense? Exactly. So and I think you might be on the right track right there. So they are, say this right here. They are not mutually exclusive, or they are mutually exclusive. So which of these is it? They are mutually exclusive, or they are not mutually exclusive? Which of these is it? They are mutually exclusive, or they are not mutually exclusive? Which of those is it? Good practice. Keep the points going. This is practice, practice, practice. they are mutually exclusive or they are not mutually exclusive. They are mutually exclusive or they are not mutually exclusive. So you have to look down here to the way of doing it. So if we know one occurs and the other cannot occur, they are mutually exclusive. If we know one occurred, they are mutually exclusive, yes. Because if we know someone passed, they can't fail. So they are mutually exclusive. And this is the same way with this question. So we can keep to this right here. We could say 90% of students pass, maybe 96, 97%. 2% of students fail and 1% of students withdraw. This is now a proper sample space because it lists out all the probabilities of everything that could occur, and the probabilities add up to 1. So we actually reviewed one of the rules right here. The probabilities of the events add up to 1. They're contained between 0 and 1. It's a proper sample space. Now, how do we check independent? To check independent, which is a totally different idea, they do overlap in some ways, but we say, I know A occurred. This influences the probability of B. That would mean dependent. This does not influence the probability of B. Independent. So if you know someone passed, if we were able to draw a picture of disjoint, yes, disjoint is the two separate circles, correct. And so how about this? If you know someone passed, is them failing that class, is their failing the class independent or dependent of passing it? And so think about how you'd say the sentence. So this actually works that disjoint events must be this, which don't blend the topics though, but it is a fact. Someone passing a class would be what of them failing it? Independent or dependent? So you have to say, I know someone failed the class. What's the probability of them passing that same class now? If you know someone failed a class, the probability of them passing would go to what? Because you know they failed. So someone's like, oh, I'm in the 2% who failed the class. And you're like, oh, that sucks. Well, I guess what's the probability of you passing is 97%, so you probably passed, right? And they're like, I just told you I failed. So is passing and failing and withdrawing independent or dependent? They are disjoint, which means disjoint events are this, which they're not the same thing. What do you think? So you have to ask yourself, I know somebody passed a class. Yes, yep. And this is a fact. Great job, Noel, right there. You are correct. Dependent because we know if they failed the class, they did not pass. So if you know someone failed a class, you know they didn't pass, which means if you know someone, like just go down here, I know someone failed a class. Well, then this totally influences my probability of passing because I know they failed. So all disjoint events are dependent. Not all dependent events are disjoint. So this is a fact of the world, and this is why you don't blend the topics. All disjoint events are dependent. As in, if something stops something else from happening, then the other thing would be dependent on it. But what about all dependent events are not don't write that, are not disjoint. All dependent events are not disjoint. So if we were to say something like, it's freezing today, like below 32, it's freezing, and it's snowing. Yes or no? It can be below freezing and it can be snowing. Can it be below freezing and snowing? So now I'm asking if one can occur and the other can occur at the same time. Can it be below freezing and snowing on the same day? So that means we're trying to check if they are disjoint or not disjoint. So what Noel said right there is if we have two circles that overlap where it's snowing and below freezing, they can both occur, or is it snowing and below freezing don't overlap, which this is not disjoint. And this is, that's disjoint, excuse me. This is disjoint. What do you think? Can it be below freezing and snowing? Yeah, exactly. And wait, so they're not disjoint. They're not disjoint. Correct. Let me see here. But are they dependent? So they are not disjoint. Just double checking my work. They are not disjoint. They have this joint right here where they can both occur at the same time. That's what not disjoint means. Are they dependent? Like, would it being below freezing influence it to snow more? Like, if you know it's below freezing, is it more or less likely to snow? If 2% of days it snows and today it's below freezing, would it be more or less likely? Would the probability of snow be influenced? Would it be dependent? So now you ask, it's below freezing. And since it's below freezing, I know it's below freezing. Does this change the probability of snow? Exactly. That's what dependent means. Dependent means knowing one thing is happening. Like, I know it's below freezing. It's more likely to snow. So the probability of snow is dependent on the temperature. And so now we've seen two things that are not disjoint, but they are dependent. But if things are disjoint, they have to be dependent, because you could do the reverse right here and do the 100-degree temperature to where you say it's 100 degrees outside. And if we say it's 100 degrees, here we'll put this, that's below freezing. We'll say above 100. So this is 100 plus. And this is 100 plus temperature. So now we are in the world where we say, if it's 100 degrees outside, can it be snowing? No. So they can't occur at the same time. It can't be snowing at 100 degrees. So that means they're disjoint. And then also, you would say it's 100 degrees. I know it can't be snowing. It has changed the probability of snow to 0. So the probability of snow actually goes to 0 because it has been influenced. It would actually bring the probability of snow down. And by the probability of snow going down, you would say they're dependent. Does that make more sense on what dependent means? It means that knowing one thing occurs influences the probability of another. That's what dependent means. Disjoint means if one thing occurs, the other can't occur. So literally by setting the probability here to 0, which goes along with the disjoint, like disjoint events are dependent. This hopefully brings the terms more sense. And then we have our checks right here to check if they're disjoint, to check if they're independent. And write these down, practice them, know how to check. So these are right here. Are they independent? No, because they're very dependent. If one thing occurs, the other cannot occur. Just a quick question. I don't like this question. I don't like this question. We'll finish off with a question I don't like. So once again, thank you, Noel. Hopefully this has helped bring some clarity to a lot of these terms. But it really comes down to knowing the terms and knowing how to use them for this chapter. Yay, you're welcome. It really is just review, review, review. And the more you review it, the easier it gets. And yeah. This one, we don't really put things like this on test 2. This is more of a test 1 type question with a contingency table. If someone doesn't like to watch basketball, I got this wrong last class. If someone doesn't like to watch basketball, I got to get one question wrong. That's the way it works. What's the probability of what? It's probably she will be a football fan. Okay, they don't like to watch basketball. So given they do not like to watch basketball, probability of football fan. I couldn't add these numbers last time. Is that 57? I think it is. So 57, and there we go. So 39 over 57. Try to do it in our head. It's almost 40 over 60, so it's going to be about 67.2, I think. I'm just doing it in my head to start. See if we can get it in our head. We get 3 guesses. Oh, that's a bummer. Okay. 39. Ooh, see, that's where I make a mistake. 68.4. Close. Sure, why not? Seeing if it gives me the leeway. Okay, so now that I've checked too many answers. There we go. No leeway on that question, which is a bummer. I like when they give you a little bit of leeway. I was just seeing if my typo would give me the leeway, but it is. The answer, once again, is seen on this page right here. 39 divided by 57. Just try to do it in my head to start, and then see if it accepted a typo for fun. Have a little bit of fun with these questions, but make sure you understand that this is just doing probabilities right here. It's just the amount of trials that occur that meet what we want over the total number, so x over n. And we actually talk about that coming up here in the next chapter, chapter 13. X over n is the probability right there, and we call it the sample probability. Yep, and that's how we got the 57. 57 is obtained. Yep, exactly. Yeah, no, don't worry. I'm putting wrong answers in here all the time. But you add up these numbers right here to get the row total, which actually makes this a conditional distribution. Given someone does not like basketball, what is the probability they like football? It's more of a chapter 3-ish question. It's a decent review question, and it deals with probabilities. But the sample probability right here, or the sample proportion, is equal to the amount of trials that satisfy over the total sample size. So 39 would be X, and the sample size is 57 right here. That is more of a chapter 13 way of writing it, but that's got it. Whole chapter 12 reviewed right here. We did a lot. We did at least one problems. So if you're looking for a really good chapter 12 review, this video goes over the law of large numbers, a lot of the rules like the complement rule. Think of the 5 rules we've got. Rule number 1, probabilities have to be contained between 0 and 1. Rule number 2, the set of all things that can occur, the sample space, has a probability of 1. The rule number 3 is the complement rule. 1 minus the probability of an event is the complement. Rule number 4, the addition rule. To add together 2 events, they must be mutually exclusive, and then we can just add them together. And rule number 5 is going to be the multiplication rule. To multiply 2 events, they have to be independent. So we choose to divide by 57. Are we looking for the chances if being a football fan? The question itself, just and double check the way it reads for you. With the question you have, if someone does not like watching basketball, so key right here, if somebody does not like watching basketball, so that I've highlighted that right there. If somebody does not like watching basketball, so that means only these people, what is the probability she will be a football fan and will be a football fan because Tennessee beat Bama? And so we get this right here, and we get the total is 57 because we add together those 2 numbers. So add them up to get the total people who don't like basketball, and then take 39 over 57. And that is equal to, technically, X over N, which is sample proportion, which is going to be 0.684. How's that look, Noah, right there? So the sample proportion, or what we see in this, is 68.4% of people who do not like basketball are football fans, because my fantasy team's going to lose this week. With that, let me save. We have saved the notes. We'll do our outro. Good work. We've got some review. We've got the full homework. Bye for now. Bye. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.